Yeah, let's start discussing what you did, for example, in this problem. What you started doing. Both in terms of, well, there are two directions, right? As you said, as you observed at Ham yesterday, there is the beginning of the solution, there is the end of the solution. In some sense, we can approach from both directions and finally try to bridge the gap. And this was the what you tried to say with this claim one, claim two, claim three example. Uh, the beginning of the solution will be analyzing the given information, and the end of the solution will be analyzing the desired information, desired statement to be proven. So the given information is, what is the given information? So there is a triangle and there is the circumcircle. So this is the base of the figure. There's not much to it. Now there's a circle omega, which is tangent at point A to uh, the circumcircle. So this is not a uniquely determined circle, right? So this circle is basically determined by its size. So we can enlarge it, uh, but it always goes through the point A, and it always has the same tangent direction. So remember that figure uh, from this one. Yeah, this pencil. So it's so one of these circles is the circumcircle, and the other circle omega is just any one of these. So it's just chosen like that. Okay. So this is the, this is how I start thinking about the problem. This is the analysis part. So there is again not much to it because this is a standard uh, a figure. But we of course need to know information about this standard part. That is, what can we say about two circles that are tangent uh, at a point, and what the rest of the figure consists of two lines going through this point, right? AB and AC. Essentially, we can see the figure like this. So we can see this as the basis, the fundamental part of the figure. Now, on top of this, so I'm trying to come up with a layered structure of this shape. You see, as I always do. I'm trying to come up with a layered structure in my mind about this shape, this figure. At the fundamental layer, I have two circles that are tangent to each other and two lines going through this point. So this is a very, let's say, standard simple part. And on top of this, what is defined is, other than these points, these intersection points KB, and this other unnamed point, maybe we can give it a name, and C. Other than these, the interesting points are the point L and point T. Then from this, well, point T is defined in terms of L. So first L is defined and then T is defined. Then regarding T, we are trying to prove something. So how can we formulate what we are trying to prove? So in terms of the analysis of the given information, we just basically come up with this layer structure, and we just tell ourselves that we need to understand these points better. This is all we can, the conclusion that we are drawing from here is that we need to understand the point L and the point T better. But better in what sense? We need to have a targeted approach to understanding. So namely, what we are trying to understand is to prove this conclusion regarding the distance bt. So this statement to be proven. Now we can focus on the end of the solution. We can forget about the beginning of the solution, but the end of the solution. What can help me conclude the end of the solution? What is this equivalent to? In geometry, most of the time our statements are if and only if. Okay, most of the time. So you can imagine that this is given and derive something from it and try to, or I mean, you don't even have to explicitly think about it that way. Basically, you are just you will just analyze this statement that the length BT is equal to the length of the tangent from B to omega. You will simply study this statement and try to formulate it somehow. I mean, for example, if I actually draw a line from B that is tangent to omega, and there are two possible lines to draw, and define that point of tangency, it's not really useful because I'm defining an extra point, then I will try to understand that point. Maybe I don't need that at all. Maybe I just need the distance, and there is a better way to find that distance without defining an extra point. If I can handle that, this will already be some progress because it will save me from defining an extra point. Any idea about this? Since you didn't solve it, I'm not directly telling you the solution. So let's actively start thinking about the problem and give me any kind of idea. Actually, I think for our classes, it is better to to adopt a model in which we try to solve the problems together. Okay, uh, together out loud. So all the thoughts that come to your mind, whether you think they're good thoughts or not, you should probably just say them. We should basically be brainstorming together. In the meantime, I want to draw the alternative pictures of this, as I told you. Let me draw alternative pictures of the same problem. Welcome, Kerem. Kerem has solved the problem, by the way, but I have not received a solution from others. So Kerem, we started discussing the problem. So I know you solved it, but it is beneficial for you as well I mean, for us to start thinking about it, trying to solve it in a real time, because we will probably end up with a solution which is somehow different from yours. Because in this problem there are so many things that can be done that solutions will not be identical to each other, and every new solution that one sees will be worth. So what I told Adhem and Abdullah is to just give me any kind of ideas. In the meantime, I'm trying to draw alternative pictures. So this part of the picture is the base, the fundamental part of the picture. Okay, and then one alternative thing we can do is to draw L on this side. You see, even with the same circle omega, you can choose another L. Maybe it is reasonable to draw them on the same picture, because then what happens is, in fact, let's call them L1 and the other one L2, okay? Because both of them are possible choices. And consequently, the choices for T are like this, T1 and T2. So in particular, both of these distances must be the same. In particular, B must be the midpoint of T1, T2 for the problem to be reasonable. Because if the problem is correct, both this distance is equal to the distance of the tangent, this distance BT2 is equal to the distance of the tangent from B to the red circle, and also this distance BT1 is also equal to the same distance. So this is already something interesting. So I'll call this pictures for the problem. Another interesting picture I want to draw is when omega is tangent from outside. Now, yet another thing could be when omega is tangent in a way that the circumcircle remains in the interior of omega, but in that case there is no tangent, so the point L cannot be defined. So that's not valid for the problem. In the real setup, it's not valid. Although algebraically, still there is no difference if one considers non-real points. Even that still falls under the same general umbrella. So let's define point L. For example, let's look at point L in here. No, not that one. Sorry. Yeah, this one is a little more complicated to find. More complicated to draw. Again, there are two points L, of course, but this one somehow is difficult to draw in the picture. Anyway, as you can see, there is not really a difference. So all of these should be just valid pictures for the same problem, same figure. But okay, the first idea in this problem is universal. I think everyone who starts thinking about this problem and who can actually finally end up solving it will think the first step will be the same thing. The first step will be common to all the solutions. But in the rest of the steps, there could be a lot of variation. But the first step is this. What is the length of the tangent? What is the length of the tangent drawn from B to omega? How do I understand this without necessarily drawing the tangent and defining that point of tangency, which is unnecessary? Because defining an extra point comes with a cost to understand that point. That's not what we want to do. We are only interested in the length of the tangent. The answer to this is what we learned about power yesterday. If we can know the power of a point with respect to a circle, if we can know the power of a point, in this case, do we know, can we somehow express the power of B with respect to omega on this figure in terms of the points that are already defined?
Yeah, we can.
What is it?
BKBA.
Yeah. So the length of the tangent is just square root of this. Square root of BK times BA. You see? This we already know because length of the tangent squared is equal to the power, as we learned yesterday. like here. The length of the tangent squared is equal to the power. So in this problem, therefore, we want to prove that BT squared equals BK times BA. So this should be the first step of starting to solve the problem. All right. So observations. Let's say thoughts. Once we start thinking about the problem. Did you think about this, Adham or Abdullah?
Yeah, but I wasn't used to anything I could think of.
No, so okay, this is the first thing. So, but then we start thinking about how we can do this. As I said, in terms of the given information, A, B, C, K are the basic points, and then L is defined and then T is defined. So we are trying to understand the points L and T in such a way that we want to understand the distance BT. How can we understand the distance BT? From this figure, well, this figure consists of circles, circles, and there is tangency of circles, uh, and tangency of a line to a circle. So this is suitable for angle chasing. In general, just in principle, this is suitable for angle chasing. But how do you, well, with angle chasing, how can you ultimately end up something with distance? You do not chase the distances, you chase the angles. But if you can get similarity of triangles, something like that, if you can get a similarity of triangles or some equality of angles, which, well, yeah, equality of angles really gives you similarity of triangles, right? So that can give you something about the distances. So we need to find a good triangle in which we see the uh, length BT, which means two of the vertices of the triangle will be B and T. What can be the third vertex? We should think about the third vertex and look at that triangle and try to do angle chasing with those triangles to ultimately end up with something that we want, you know, something like this. We can try to formulate this in terms of triangle similarity first, okay? So this is the second thought. In order to get this equality, in terms of length, we can formulate it as triangle similarity. Okay, this is the way to convert angles to lengths. Because when you have angle equality, when you have two triangles with the same angles, you have the ratios of the lengths equal. And from this, you can obtain something about lengths. Or if you have information about lengths, you can obtain similarity and you can get information about angles. Or conversely, if you have information about angles, you can convert it to information about lengths. In this case, getting information about angles looks easier because there's a lot of tangency and stuff. We can do angle chasing. In order to get this equality in terms of lengths, we can formulate this triangle similarity, hence angle equality. Triangle similarity can be done with angle equality. Then we can do angle chasing. Then we can do angle chasing with tangents. So if we can start doing this, we will start bridging the gap. So part of this will be, first of all, how can we formulate this as triangle similarity, and how can we, formulate this as angle equality? This is the first thing. And then secondly, how can we obtain angle chasing from the given figure? Now, any idea? Well, let's really just think out loud, okay? Let's brainstorm together. Kerem, you can also speak, because if you say something which is not exactly the same as your solution, then you can also say your ideas. I want all of you to speak. Well, first of all, how many triangles are there with, well, in order to understand the length BT, my triangle must have B and T in it. So BT something. The third point. What can be the third point? Here, of course, BTL is not a reasonable triangle. Which ones are, I mean, BTL is not good because BL, this line, I have no information about it. But BTK and BTA are good because this line is the side of the triangle, and we know we can do angle chasing with it. Right? We can look at BTK and BTA, these triangles, and indeed the length BK and BA appear here. So this looks very promising. So I can use the triangles BTK and BTA somehow, and if there is, some sort of similarity there, with appropriate ratio, length ratio, I can obtain it like this. So I can formulate this as angle equality. How can I do this? Think about it. Yeah, this I will wait from you. Any one of you can say it if you find. Did you understand my question? I want to repeat it. I know what I want to prove in the problem, but what I want to prove is not in terms of angles. It's in terms of lengths. So I want to change this to something in terms of angles, because then I can prove it with angle chasing. Because then, I will think about how to prove it with angle chasing. Of course, not every problem can be solved with angle chasing, but this one, we are trying it. We are trying to do it with angle chasing. If it doesn't work, we can try something else. We can always try something else. You can, you will always have to try various things until it works. But in this problem, because of this circle omega being tangent to the circumcircle and also being tangent to the line CL, these two tangencies is motivating for angle chasing. Okay.
One, I think that we should use the fact that omega is tangent to the circumcircle of ABC by drawing the common tangent to both of them, so we can use this fact.
Yeah, well, yeah, when we start doing the angle chasing, we will use it. But we have not started doing the angle chasing yet. What I mean is this. First of all, before starting the angle chasing, I want to know what is my target. What do I want to prove with this angle chasing, right? Right now, I still don't know it. Right now, I know my target, but it is not in terms of angles. It is in terms of lengths. So I want to reformulate my target in terms of angles, and then this will set a goal for me. I will start trying to prove it with angle chasing, and then I will do what you say, of course, Kerem, because yeah, when you have two tangent circles, and when you want to do angle chasing with it, it's reasonable to consider the common tangent line. But that's, after you start doing the angle chasing. The first thing I want from you is, what is my target? What is this equivalent to in terms of angles?
Yeah, we want to show that triangle BKT is similar to triangle BAT, or maybe.
Yeah, okay, exactly. Yeah, something like this. All right, let's write it exactly. So this is.
But it's not equivalent, it's just sufficient.
Well, in fact, it is equivalent. Think about it. Why not? Well, okay. What's your thought? What's your thought that it's just sufficient?
Or actually, it's equivalent because that they share the angle ABC.
Yeah, exactly. This is why they share the angle ABC already. So this is, so this, what we want to prove is, what we want to prove is this thing is just this, BT over BK, BA over BT. We can formulate it like this. But why did I think about writing it like that? As I said, I want to use the triangle BTK and triangle BTA. I already decided that I want to use triangles with two vertices, B and T, and the third vertex something. And the most reasonable things in the figure are K and A, BTK and BTA. And I can separate this. So I can separate this statement. Well, I can try to write length ratios in these triangles. And the lengths that appear here, BT, BK, BA. So obviously length ratios are this, BT over BK and BA over BT. And this is precisely the equality. Now, if you look at this figure, so this angle is common. And BT over BK ratio being BA over BT ratio. So if you have a common angle, if you have the same angle and the same ratio of sides adjacent to that angle, this is angle similarity, if and only if, right? So this is if and only if, and this is if and only if. If and only if what? BTK similar to BAT. And now I can write this in terms of angle equality. So this is if and only if already one angle is common. So if there is one more angle equality, that is enough. What angles I can write? I can write either BKT equals BKT equals BTA, right? Or I can write, I'm not even looking at the picture, you see, I'm just reading it from here. BKT equals BTA or BTK equals BAT. It's if and only if both. I mean, we don't have to prove both. It's just proving one. So it's if and only if this, and it's if and only if this. So we just need to prove one of these, okay? Because then, because TBK is already ABT. TBK is already ABT. So this is common angle B. So if there is one more angle equality, then they are automatically similar, and this ratio holds, and I get what I want. So you see, now one of these is my target. Now I can start doing angle chasing with the goal that I want to prove one of these. But maybe I can choose, I mean, I don't have to restrict myself to one of these, but I can, it's good to think which one of these angles, angle equalities could be easier to prove. Like we did yesterday. Exactly. So let me draw this part of the figure. I'll draw another picture again. In order to not complicate ourselves, I redraw the picture over and over again. I think this is good practice. Okay, it's good to do this, because if I draw everything on the same picture, then I will, after some point, I will start not seeing. So this is L. And this is T. Okay. One of the angle equalities is BKT, BTA. So let me show this one with green. So this angle with, so this will be definitely drawn at the end. So this green with this green, I can do. Or I can do the other one. This is with orange, BAT with BTK. This orange with this orange. Somehow, what is your opinion about whether the orange angles are easier to chase or the green angles are easier to chase? You can start chasing them. By the way, let me also tell you something else. Another way to see this whole thing, instead of triangle similarity, there is a shortcut way to think about it. Namely, it is this: BT squared equals BK times BA. This equality is equivalent to saying that AKT circle is tangent to the line BC. Can you see? The circumcircle of AKT, because if it is tangent, if you imagine the circle, I don't want to draw it to complicate it, in order to not complicate. If you imagine the circle AKT, BK times BA is the power of that, and if it is tangent, BT squared is also power. We would get this equality. And converse is true, because if it is not tangent, then the power would not be BT squared. Power would be BT times something different from BT. So this is equivalent to this tangency. And you can think about this circle and its tangency. Then these angles, this green and orange angle equalities, are simply angle chasing with tangent lines. So orange angles are what the angles that see the arc KT, and the green angles are the angles that see the arc AT. This is alternative way to think in terms of triangle similarity. And in fact, as you know, power equality is proven by triangle similarity with angle chasing.
But the same this solves the problem when we will know that BT is tangent to the circumcircle of AKT.
Yeah, sorry, can you say it again, Kerem?
Because if we know that BT is tangent to the circumcircle of AKT, then we know that angle BTK equal to angle KAT.
Yeah, well, this is, yeah, we don't know this. This is what we want to prove, right? This is what we want to prove. Because what we
That
want to
BT
prove
is
is this.
tangent. Oh, we know this because or we don't know it.
Yeah. What we want to prove is this equality, BT squared equals BKBA, and this is the same thing as saying that the circle AKT is tangent to BT. And then this is the same thing as saying this angle equality.
Yeah.
So I'm basically, again, coming from this step to the last step without doing the triangle similarity. I am doing the doing in terms of tangency of circles and power. But if you look at the, well, if you look at the inside of this, how is this, power equality is proven? It's proven with, again, triangle similarity with angle chasing. So ultimately, this is already the inside of that argument. It's just the same argument covered up in a different disguise. Anyway, so now what is my question? Let's start doing angle chasing. But let's have a target. Do we really want to prove the orange angles, or do we want to do we want to chase the orange angles, or do we want to chase the green angles? Or let's just start trying to chase both of them and see which one we can chase easily. From the circles and the tangencies, look at them. First of all, at this point T, it is more difficult to chase because we don't have anything at the point T, at least in the beginning of the problem. I mean, we don't have a circle, for example, that passes through point T, right? So these angles are difficult to chase anyway, because to really move an angle from a vertex to another vertex, you basically need a circle that passes through there, or you need another line which is parallel, for example, that intersects those. Yeah, if you have a parallel line, or if you have a circle that you can chase. But how about this green or this orange? Here we have some circles. We have a circle that passes through K, and we have some circles that passes through A. Can we chase the green angle or the orange angle from these circles? Well, let's just look at this. For example, let's look at the orange angle. If you want to chase it from the circumcircle, you need this. Well, this side intersects the circumcircle at B, and you need this side, and you need this intersection. Unfortunately, you don't know this intersection. So if you want to chase it, you will need to use this point. If you want to do it on the red circle, similarly, you will want to use this point. Unfortunately, we have not defined those points, and we don't want to define extra points unless we need. Because really the difficulty of the problems is in defining extra points. Somehow in some problems you definitely need to define extra points. But those are the more difficult problems. The more extra points you have to define, the more difficult the problem is. And somehow there is just a way in a lot of the problems to solve without defining extra points. So how about the green angle? Can you chase this from the red circle? The sides of the green angle are KA and KL. So they intersect the circle at two known points. This is good. This is arc AL. So I can simply move this green angle to another vertex on the red circle. But I don't know another vertex on the red circle. So at some point it's clear that I will have to define some extra point. So which one is the best thing? This is one way to think, okay? So if I want to chase this orange angle, maybe I will have to define this extra point. If I want to chase this green angle, I will have to define another extra point. Possibly. We have to think about those. On the other hand, so this is the end of the solution. This is the end of the solution because this is the target equality. and there will be the beginning of the solution, chasing what is given. So on the one hand, we want to chase what is given. On the other hand, we want to chase back what is desired, and we want to bridge the gap. We can think about both of them at the same time. Regarding chasing the end of the solution, this is our picture. Regarding chasing the beginning of the solution, let's analyze the given things. The given figure, the basis of the given figure is, first of all, the two tangent circles, okay? So let me write this as item 3. Let's study the basis of the figure. Well, let me not use the word basis because it appears formal. Let's study let's say I don't know what's the base layer. Yeah, let's say base layer. Now, what I call base layer is the standard figures that keep appearing in all sorts of problems. So here, this is what we have. We have two circles tangent, and we have two lines like this. This is a very standard figure. This by itself is something that has to be known. So Olympiad geometry is sometimes called synthetic geometry. Synthetic means you synthesize. Do you know what it means to synthesize? So you have pieces of knowledge and you bring them together. You combine them to generate new knowledge. On the one hand, you need to have an encyclopedia of different basic pieces of knowledge in your mind. And this is something that grows over time as you solve more and more problems. For example, this is one of the standard figures. Two tangent circles with two lines like this, one of the standard figures. And there is a standard angle chasing argument that one can do here. So if you draw this line, this tangent line, and look at the angle that this tangent line makes with any of these two lines in both circles. So look at this line, for example. This angle is equal to this angle from the big circle. It's equal to this angle from the small circle. So this shows that these two lines are parallel. And this is if and only if. Right? Let me use a generic notation, in fact, for this. X, Y, P, Q. So APQ and AXY are tangent if and only if PQ is parallel to XY. See, this is something standard and that can come up anytime. And this is how the light blue line is just used to justify this. But this itself, you can already think of this as a theorem. You can directly use it. But if you want to, of course, if you want to use it, you will just use the blue line. But it is better if you want to use this in the problem itself. Instead of defining the tangent line in the problem and try to prove it in the problem, it is better to write it as a separate statement. Then everyone knows that you have a better understanding of geometry. Just write it as a separate statement, call it a lemma. In general, we have such a fact, APQ and AXY are tangent if and only if PX and PQ and XY are parallel. And the proof of this fact is through drawing this common tangent line. Then I can come and use this fact here. And when I use it now, I don't have to draw the common tangent line. You see, what is the purpose of this? I don't complicate the figure. I don't put everything in the same picture. I don't put everything in the same figure. There is some piece of information that I want to use. So for example, I can define this point now because it is useful. If I have information about a point, then I can define it. It's not costly. In fact, it is advantageous because I already have somehow my tablet got disconnected. I don't know what happened. Okay, let's define this as M, for example. And I know that Km is parallel to BC. Okay, which one? Now defining M, okay, I defined an extra point, but it is justified, as I said, because now this point is on the red circle, but it's also on a parallel line. It's not only on the red circle, but it's on a parallel line. It's on, on a line which is parallel to BC. And this is at the intersection of this. Well, it passes through, it's also on the side AC. So it's at the intersection of three things: side AC, a line which is parallel to BC, and the red circle. So we can use this point M in angle chasing. All right. So if we come here, we see M here. So apparently we didn't draw it well, but let's draw it well now. So M should be here basically. So this is the third thought. So far these are our thoughts. Let's try to complete this. This is how we synthesize our solutions, right? We take the problem, we analyze the problem, we divide it into pieces, and then once we obtain pieces that we understand, that we know, we synthesize them back to obtain the solution. This is how Olympiad geometry works. So let's try to do it in this problem. This is a good problem. This is IMO level, by the way. This problem is IMO level. At least problem 1, problem 4 at least. And once you really, well, geometry is in some sense easier than the other areas, in the sense that once you learn how to do it, it becomes easy. But in the other areas, even if you learn how to do it, there is still a lot to do. There is still problems that you don't know how to approach in combinatorics, for example. But in geometry, once you learn about it, it almost becomes mechanical. So let's try to use everything that we have. This is our target angle equality. Target equality is this. And given equalities are here. The circles parallel lines. Well, now the tangency of the circle is not needed anymore because it's just this, it's the equivalent to parallel line. So basically, K and M are 2 points. So orange line is an arbitrary line which is parallel to BC. You can think about it like this. An arbitrary line which is parallel to BC is drawn and it intersects the sides at K and M. Then the red circle is simply the circumcircle of AKM. It will automatically be tangent. So tangency is not any information anymore. The information is in the parallelness. Of course, you don't know which information you will use. Maybe you will use the parallelness, maybe you will use the tangency. But parallelness seems to be more tractable.
Also, parallel by homotopy, we can since this is the extension of the game two lines.
Sorry, what? I didn't understand.
MK is also parallel to BC by homotopy since they both share a center A.
Oh yeah. You can prove this parallelness. Yeah, you can use this lemma by homotopy as well. Yeah, that's true. You can use the lemma by homotopy because if they are since they are tangent, there is a homotopy at the center A, which sends the red circle to the black circle, and this homotopy will send point P to X and point Q to Y. Therefore, it will send line PQ to line XY, which means they are parallel. This is also a proof. That's good, without angles. But it's a proof of this lemma. But now we are convinced that we will use this lemma in the problem. So we are back to the problem. We don't have to continue discussing the lemma. We are just back to the problem, and this is what we have. We have the points K and M on the sides, such that KM is parallel to BC. And we have point L on the circle AKM such that CL is tangent. We have these two things, and point T on KL, on the at the intersection of KL and BC. We want to do angle chasing in this figure to ultimately obtain this. So we can start chasing the angle from the beginning or from the end, try to bridge the gap. For example, Edham, this is an example of a thing in which you do something in the beginning of the problem and something at the end of the problem, but the middle is not proven. So this is basically something like what you said yesterday. And it is possible to get marks from this. It's possible to get marks from, although in this case, in IMO, they don't give partial marks very easily. They really give partial marks if something very substantial has been done. Sometimes, usually 1 point is given to things which, with an honest assessment, can even be considered to be half of the solution, right? In terms of the ideas, in terms of the effort that's spent to it. Sometimes you come to 50% of the solution in your mind, and the rest is just as difficult as what you have already completed. But in terms of partial marks, you just get 1 point or something. That's very typical. So partial marks is not our goal. Our goal is to really solve the problem. However, sometimes when you cannot complete, partial marks are also good. They just come from your honest effort to solve the problem. Okay, tell me anything about chasing these angles from here or here. Anything that comes to your mind. I mean, if you are really sitting in the exam right now, you should be thinking, and whatever you think, just tell me out loud. I think this is a better model for our lectures now.
We can show a lot of cyclic quadrilaterals.
Yeah, tell me. What do you show? Yeah.
Uh, we can show that ALTC is cyclic.
Very good. This is very good. From these parallel lines, you can show ALTC is cyclic by let me immediately show it, and I will also do this in generality, okay? So when you have generality, this is how it appears. That is, it's like this. Well, another standard figure.
You can show it since by the first cyclic quadrilateral CAL is equal to MKL. Then since MK and BC are parallel, then MKL plus CTK are 180. So
Yeah,
it follows
I
that
can
CTK, CTN.
exactly. I can imagine how you prove it, but I want to show something. You know, what is really not appreciated very much is there are a lot of Olympiad students. I've seen good Olympiad students. They solve a lot of problems, but they keep doing the same thing without realizing it's the same thing. So somehow it is good to go up one level and to understand these as standard figures that just keep coming up in different pictures. The standard figure is this. You have two circles intersecting at 2 points, and you just draw arbitrary lines from them. Okay? Just one line here, and another line here. So this is X, P, Y, Q. The statement is X, Y, and P, Q are parallel. The proof is just this. This angle is equal to which angle? It's equal to this angle from the left circle. When it is chased, it's chased to this. It sees the arc AY. Well, you just basically look at the line XY and look at the angle that it makes with one of the red lines. It doesn't matter which one. Just take this one. So this one sees arc AY. So I move it to the other point, B. The proof is automatic. I don't even have to think about it. Now I came to this circle. Now this sees the arc AQ, so I will move it to the other point P. It will move here. Now you see, they make the angle with the same red line. So they are parallel. This is one standard figure which keeps coming up. Let me show you the different ways in which it comes up. Different pictures. Sometimes it comes up in the way that we are given one of the circles and the other circle is not given. The points are given, but we don't know they are cyclic. Instead, we know that this is parallel. Then we can invert the logic and we can prove that it is cyclic. So let me draw different pictures of this. How can we draw different pictures? Like we can have the circles intersecting like this. And we can have the red lines, for example, in this fashion. So P and X are not on different sides of A here, but P and X are like this. And for example, this can be like that, Q and Y. Notice the naming is consistent. There are two arbitrary red lines, one going through A, one going through B. And the line that goes through A will intersect at P and X. And the line that goes through B, it will intersect at Q and Y. But P and Q will be on the same circle, and X and Y will be on the same circle. So here also P, Q, and XY are parallel. The conclusion is the same. Even though the pictures might look different, the proof is ultimately the same For the proof, I just need to look at this blue line and the angle that it makes with this blue line. I will chase it from this circle. It will come here. Now I will chase it from the small circle. It will come here. Yet another picture. One of the red lines can be like this, and the other red line can be like this. I want to always, guys, teach you the general facts that keep coming out of the problems. So this is Q and this is Y. You see PQ and XY are still parallel. And how do we prove? So we have this angle. If you chase it from this circle, AXY, circle of AXY, chase it to point B, it will come to this angle. It will come to this angle, right? So it's the opposite of, it's the complement of angle ABQ. So if you chase it from this circle now, ABQ, so it sees the arc AQ from this side. So it comes to here. You see, again, you see parallel. Of course, the same thing. So this is another standard figure. I want to put this into a box. One common way that we use it is, as I said, so it doesn't always come in the form of two circles. It usually comes like one circle, ABXY, one circle, okay? And 4 points, ABXY, cyclic. 4 points on a circle. And then some line PQ, which is parallel to XY. Then AX intersects it at P and BY intersects it at Q. Then we will know AB PQ is also cyclic. So let me also draw it in this fashion, maybe. Just 4 cyclic points, A, B, C, D. And there is just some line, which is some green line, which is parallel to CD. Okay. AC intersects this at K. BD intersects it at L. Or maybe, let me not call them C and D. Let me call them, it's better to call them R and S. Okay. Here ABKL is cyclic. This is in fact the same lemma, just with opposite logic. So if I know that ABKL is cyclic, I will obtain RS is parallel to KL from the above figures. But if I instead know RS is parallel to KL, then I will obtain that ABKL is cyclic. Because this time the proof will be again, we will have both lines making the same angle. And when we chase the one that's on the circle to this side, it will be chased here. And since this angle is equal to this, ABKL is cyclic. So let me put this into a box. So if we go back to our problem, exactly we see this figure. There is a circle, ALKM, and one of the chords of the circle KM is parallel to another line outside, BC, and KL and MA intersect this. You see, intersect this line. So there is this line outside, which is parallel to KM, and K is connected to L and intersects this line. M is connected to A and intersects this line. So K and M will be replaced by these 2 points. T and C, ALTC will be cyclic. It's exactly this figure. And the proof will be the same, of course. The proof will be, the proof that you are saying to prove that ALTC is cyclic, what we can prove is ALK, the angle ALK, equals AMK, which is ACT. And this shows that ALTC is cyclic. Was this your angle chasing?
Yeah, it's the same thing. I just used
Yeah.
KL instead of AMK.
Yeah. So, okay, yeah, I did. Since I wanted to discuss the general thing, I went to this whole discussion. But remember where we came here from. Ethem just said from the given figure, when we start thinking about the base layer of the figure, where we have this shape, from this we can obtain ALTC, and from these parallel lines, we can obtain that ALTC is cyclic. By the way, in proving that ALTC is cyclic, L is just an arbitrary point on the red circle. Here we have not even used the fact that CL is tangent. For any point L, arbitrary point on the circle, if you can define T as the intersection of KL with BC, you can obtain that ALTC is cyclic. So here, what we use is parallelness of KM to BC. Now somehow we will need to use the tangency of this as well to prove further angle chasing. So let's write this. In the problem, we find ALTC is cyclic. How? So there is this red circle. Basically, this arbitrary blue line intersecting at L and T. Because this angle equals this, and it's equal to this. This is something very good. Okay, let's remember, this is our target. Now this green angle can be chased here. Because now there is a circle. But the orange angle also can be chased. I don't know which one is better to chase. Because there is a circle which passes through the point T. And the circle is ALTC. The orange angle is LTC, the complement of LTC. So it sees the arc LC. The green angle is the complement of this, so it sees the arc AC. Both of them can be chased, really. This information, after this information, this ALTC is cyclic, very good information. This very good information can help us chase either of these angles. Either we have to move this orange angle to here, or we have to move this green angle to here, right? If we can do this, we will bridge the gap and solve the problem. So please use that ALTC is cyclic to move these angles. What can you do? So Abdullah and Kerem, you are also thinking, right? Because Kerem, your solution was different. Your solution was also a beautiful solution. But now, as you can see, we have moved in a different direction. All right, anyone? What are you trying to do?
We have by tangential of CL, we have that angle CLM equal to angle LAE. Maybe we can use that. We want to show that angle B. If we show that angle BAT equal angle LAE, I think that will be sufficient.
BATLAM. Yeah.
LAM.
Yeah. I mean, what you did is basically you chased. So here's what you did. So you chased this orange angle to, because ALTC is cyclic, this orange angle will be chased to LAM. Right?
Yes.
Okay, then how can we use it? By tangency or something? How can we?
We
Okay,
have
let's start. Let's start doing it. Uh, let's start doing what you're saying. So you want to chase the orange angle. Fine. You see, already this shows us that this problem will have more than one solution because there are different paths we can follow, and probably all of them give rise to the solution. The problem doesn't have one solution, right? So I'm trying to draw this figure, this picture, and do the angle chasing. So there is points KM parallel. There is the circle. Maybe the circle itself. Yeah, let's just put the circle. And there is the point L here on this circle and at the intersection of the circle and KT. What we know is CL is tangent. What we know is that CL is tangent to the circle that we have not used yet. So you are saying let's start chasing this angle. This angle, as you can see, is made between the lines LT and TC. So it's the complement of LTC. So it can be chased in the circle ALTC. It can also be chased by the parallel lines. Now, in the beginning, we were not able to chase these angles because we didn't know anything about T, because there was no circle passing through T and there was no line through T that is parallel to something. Now we have both of them. We have a circle and we have a line that's parallel. We can use both, I guess. If we want to do it with parallel, it will be chased here. Right? And now maybe you can use the circle to move it here. Or you can directly use the circle ALTC to chase this orange angle here, which is fine. Directly. So this, okay, we already know, but this is not what we want, right? We want KAT. We want this one. So how can we further move? Maybe
Actually, I think
if we use the tangency now, that would be good, because this is the angle arc LM. With tangency, we can move it to this. Although I don't know if this is necessarily good.
actually I think that we can do it in another way. We have angle CLT equal to angle KAL by tangency
CLT equals
KAL by tangency.
I'm trying to understand this way. CLT is this angle. Yeah, that's true. So this
Yeah,
angle.
and we
Okay,
yeah, and
let's do it. So this one, this purple one is this one, which is
yeah,
this, of course.
and we also have
So what you're trying to
since
prove then, okay. So instead of, so you're saying moving this orange angle to KAT is the same thing as moving the purple angle to this TAC, right? Because
no, actually I'm not trying to prove this. I want to prove something simpler. We have we have that KAL is TLC, and also we have LCT equal to LAT, since ALTC are consecutive.
that's true. By
And so
adding
yeah,
them, you can obtain the orange angle.
yeah,
Okay. Yeah, this is also. You see, there are countless options.
yeah,
So this orange one. Okay, the other oranges are not necessary then. So let's go back to all of this. So this, you have not used it at all. I see. So what you have used is a different approach. So you have countless options. You want to chase this. This is also possible. That's true. Sometimes we don't chase an angle directly. We separate it into two angles. We chase them separately and we combine them again. This is a very good thing. So what Kerem has done in chasing this orange angle, still he's trying to chase this orange angle to here, but sometimes you can divide it and combine. It's possible if this is easier to chase. So what Kerem has done is to separate it into this purple and this, let's say pink, which can be chased from their circle. So this, for this one we can use ALTC. So with the orange one we can already use ALTC, but the advantage of separating is with the purple one we can use, instead of ALTC, we can use the tangency. Because at some point we will need to use the tangency in chasing, okay? For sure, at some point we will need to use the tangency. So you can start thinking from here. How can I use the tangency in chasing the angle? And any angle chasing you do with tangency somehow is reasonable. So we have to take this line, this tangent line, and look at an angle that it makes with one of the lines. Okay, for sure, yeah, we have to take this tangent line and look at the angle that this makes with either LK or LM or LA. There are three options in the red circle. If I want to use the tangency, I'm just being logical. If I want to use the tangency, because I don't want to make this idea of dividing look top down. It's not top down. It's a very natural idea. Because I know in this angle chasing I will need to use tangency because I have not used it so far. And there is this tangent line. So black line and red circle. I will need to use this. How can I use this? The angle, I have to use an angle at the point L. The angle must be between the black line with some line going from L. Either LK or LA or LM. There are three options. So let's just use one of them and see whether it works. What Kerem has done is let's just use LK. Okay. See how I can chase. That's the idea is simple. So let's just use this purple angle. From tangency, it is chased to here. Then the question is, okay, how can I use this to chase my angles? Because my angles are these, orange or the green angles. So if I want to chase the orange angle, what's the connection between this orange angle and the purple angle that I got? Well, I want to chase, I have the orange angle here and the orange angle here that I have still not connected, but I know that the purple angles are connected. So I want to, so I know that the purple angles are the same, but I don't know this orange angle is the same as this orange angle. This is what I want to prove, right? The orange angles. So is there any relation between the purple and the orange? Well, the relation between this orange and purple is clear. It is this pink. The relation between this orange and this purple is this one. But they are the same because of ALTC. So this pink can be moved to here. And it can help us connect this purple to this orange. So this is one way to do the angle chasing. There are many other ways. Many other ways. So let me write this as a solution, ultimately. You see, I've used this problem so many times in my training, several times in Turkey and in other, in my training of the Turkish team, the Saudi team. I use this problem a lot, and every time I use it, a different solution comes up. Although all of them definitely starts with this. So this is definitely the common idea. Somehow you have to convert it to angles. And you have to do angle chasing. That's common, but the angle chasing part can be done in so many different ways. But this cyclicity of ALTC is also common to all the solutions as far as I can see. So, okay, this has been a collective effort solution. Very good. So let me write the solution. So from the beginning, we have to say everything, okay? We have to summarize everything. First, let M be the intersection of second intersection. First, we defined M, right? We have to write it. Let M be the second intersection of omega with AC. Notice I need to say second intersection because a circle always intersects, well, a circle intersects a line twice, and one of the intersections is A already, so the second intersection is M. What we know about M is Km parallel to AC. In a real solution, you have to explain this, but here I'm just writing angle chasing because I don't want to waste too much time. The second thing we obtained is, notice when I start writing the solution, I don't want to write the end of the solution in the beginning. I want to just start from the beginning to the end because this is a cleaner way of writing it. So reordering all the thoughts. All the thoughts are here in a complicated order. I want to reorder them in a good way. The first thing we found is this point M. Now using this point M, the next thing we found is cyclicity of ALTC. ALTC is cyclic because where is it? Yeah, it's here, these angles. ALK equals AMK. Well, ALK equals AMK, which is equals to ACT. Therefore, ALTC is cyclic. Now, the next thing I need to do is use ALTC cyclic to do this angle chasing. This is the third thing I need to do. Namely, LAT equals LCT. LAT equals LCT. And so this is the pink angles, and the purple angles is KAL. KAL equals TLC. KAL equals TLC. This is because CL is tangent. Tangent to omega. This is because ALTC is cyclic. This is good. I mean, this is because KM is parallel to TC, right? So when we add them, this is KAT. KAT equals KAL plus LAT, which is equal to TLC plus LCT, which is equal to LTC. I mean, complement of LTC, which is LTB. Yeah. Which is KTB, right? I can just write KTB. KA. So I came here. Now I can say that this is similar. Okay, now I can say
How is KAL equal to TLC?
so KAL is the angle which sees the arc KL, right? In the red circle. So this is the angle. So you can move it to point L. You can move the base point to point L. Then it will be the angle between KL and the tangent line. So if you just put any point X here, KLX. So it's like this. So there is L, there is X. X is any point in the extension of CL. And there is K. So this purple angle is the angle which sees the arc KL. So it's equal to this angle. So what is opposite to this is if you look at the extension, so there is C here and there is T here. So this purple is also seen on this side. Is it clear now? Or no?
Yeah.
No. Okay. So now the fourth thing is, after observing this angle equality, we say KAT equals KTB. Well, instead of KAT, let's write it as BAT. BAT equals KTB, and at the same time, of course, ABT equals let's write this as BTK, right? Let's write this as BTK. ABT, so ABT equals TBK because they are both angle B. So from this, you obtain BAT. Triangle is similar to BTK. From this, you obtain BA over BT equals BT over BK. So from this, you obtain BT squared equals BK times BA, which is power of B with respect to circle omega. Therefore, BT is equal to the length of the tangent. Tangent from B to omega. This is how the full solution has to be done. As you can see, now this is in order. However, the thinking order is not this. The solution writing order is this. Thinking order, we first started here. We observed this angle equality. This was the first thing we thought. This was the second thing we thought. This was the third thing we thought, and this was the last thing we thought. But the correct writing order is this.
Actually, I think that we can do it alternatively because we have angle BTK equal angle MKT since KM is parallel to BC, and also we have angle
Wait, say it again. BTK equals
BTK equal to angle
MKT.
TKM.
Yeah, this one, yes. TKM, yeah.
Yeah. And also TKM equal to LKM, which is equal to LAM.
Yeah.
And so angle LT, LTB equal to angle LTM, LTC. And so BT is tangent to the circumcircle of ATC. And so BT squared equal to BK times
I don't
BA.
understand. Wait.
Or,
Sorry, you
or,
moved.
or,
You are trying to do with the orange angle. So this orange angle, you moved it here. Then what? And
no,
then
actually,
you moved it to then you moved it to here. But how can you move?
actually, I think there is some mistake. I thought that K is circle. So
Okay, it's fine. Yeah, but there are many alternative ways. Many alternative ways. For example, let's not waste time by writing them, but what you can do is, for example, instead of looking at the pink angle, you ignore the pink angle, you can look at the purple angle, and after moving it to here, so this purple is equal to this, still the same thing. I start with the purple. Continue chasing it. Chase it here. Okay? TAC. So since this purple is the same as this purple, their complements are also the same. Right? If this purple moves to this, then KAT moves to LAM. So AL and AT are symmetric in the triangle. Symmetric with respect to the angle bisector of the triangle. KAL equals TAC. That means KAT equals LAC. So after moving KAT to LAC, then you can immediately move this angle to this orange angle from ALTC. This is also a way to do it. There are lots of ways. Lots of ways. Your solution was also good, Kerem, and let me try to again verbally formulate your solution in this framework, in this way of thinking, to let your friends know about it also. So, of course, the idea should be the same. We need to get the length equality from angle chasing, but Kerem didn't start with this one. Instead of writing it like this, he wrote it like BT squared over BK squared equals BA over BK. This is also something you can write, right? BT squared over BK squared equals BA over BK. Let's try to prove this. Now, this is not immediately similarity, but this is something we can prove with similarity. On the left side, we have the ratio of BT, BK. So this can be something we study with from the triangle BTK. But the right hand side is BA over BK. So there is no point T there. This is easier. So how can you chase BA over BK? From parallelness, BA over BK equals CA over CM. Now, how can you study CA over CM? Again, using this tangency and the same angle thing. This is equal to the square of CA over CL, or CL over CM, which are the same thing, or AL over LM. So BA over BK is equal to CA over CM, which is equal to the square of these ratios. On the other side, we are trying to prove that this is equal to BT over square of BT over BK. So one thing we can do is to prove that BT over BK square is equal to AL over LM, for example. And why is this ratio especially good? Why we are choosing AL over LM? Because the angle ALM is equal to AKM, which is equal to angle B. So when you are trying to prove this ratio of two sides equal to ratio of another two sides with the same angle between them, this is triangle similarity you can do. This was Kerem's solution. So to prove that this triangle TBK is similar to triangle ALM. And this is something you can do with angles immediately, because BKT, angle BKT is equal to angle AML. In this, you don't even have to observe that ALTC is cyclic in this proof. Yeah. This is just an alternate phase. So there are really 20 solutions, more than 20 solutions for this problem. Only this is common to all of them, but somehow you have to convert the length thing to something with angles, and you have to do the angle chasing. This problem is IMO level for sure, and the IMO geometry problems are also like this. You basically divide the problem into chunks. You start thinking about how you can obtain this, how what this is equivalent to, how you can chase this angle, how you can obtain this length ratio equality, etc. You start thinking, you start analyzing and dividing like this, and ultimately you come down to the standard stuff that you know, and it becomes synthesizing this standard stuff. Sometimes you may not know this standard stuff, but you just discover it by yourself without realizing. You just discover it. For example, Ethem observed that ALTC is cyclic. Maybe he didn't observe that it is just this general fact, but he just observed it in the problem. This is also very common. Usually it happens like this. We observe something in the problem, even if we don't know. Sorry, I had to turn off my mic. So then, what was I saying? Yeah, we synthesize these pieces to obtain the solution. Did I forget to say anything? Sorry, my little son just interrupted the lecture. This is why I had to go out. Yeah, I think I completed what I was gonna say. Yeah, in IMO problems also. Yeah, what I was gonna say is it's just that the IMO problems also work in the same way. Okay. So I believe these problems should give you confidence, inshallah, should give you confidence to attack the IMO problems. So if you do the shortlist problems, try to do the shortlist problems by yourself, G1, G2 level shortlist problems. Essentially, you obtain the solutions in this way. Okay, do you have any remark? So in fact, my intention today was to quickly discuss the solution of this problem and then pass to a discussion about triangles. But we have spent too much time on this, but still we can do our discussion about the triangles, because we can have at least 1 more hour. Maybe we can take a break, by the way. We can take a 10-minute break. That could be, in order to not get tired, that could be better. Do you agree?
Yeah, that works.
Yeah, that's it. So let's take a 10-minute break, and then in the second session I will do triangles with you. All right. So today I want to tell you these basic theorems of triangles, some of which I'm sure you know, but I will nevertheless tell you about them, as I told you about power of a point with respect to circle and radical axis and this kind of classical stuff yesterday. So I want to tell you about this classical stuff about triangles, because it is the way that I tell, I think the perspective in which I tell the subject will nevertheless be novel for you. But after this, we may not have time for problems, and we can we can continue doing the problems in our next lecture, hopefully, inshallah. So let's put our title as basic triangle facts. Basic triangle facts, triangle configurations. Okay. So simply we have 3 points, and points defined in terms of these 3 points. But we don't want to have too many points, right? So these are the basic configurations. If we have too many points, then this is already like an Olympiad problem. So, but when we have a few points, these are the standard figures that we must just learn, we must just know, and we must use them in our synthetic solutions. Basic triangle configurations. This includes just 1 point defined in terms of the triangle. So these are called special triangle centers, such as centroid, orthocenter, circumcenter. These are the most basic ones. So I want to first start discussing them. First, let's talk about this, circumcenter, circumcircle. Well, the fact is, any triangle has a unique circumcircle. Given 3 points that are not collinear, there is a unique circle passing through them. So statement is, well, and this, okay, this will have a center, of course. The statement is, let A, B, C be not collinear, then there is a unique circle passing through A, B, C. How can we prove this basic fact?
We can start by assuming the contradiction that we have 2 circles inscribing this triangle.
No, we first of all have to prove that there is a circle, right? Maybe there exist 0 circles like this. By the way, can you remind Abdullah to join the lecture also? But first of all, we need to prove that there exists a circle. Well, the approach is, first of all, let's find the center, then the circle will automatically be found, because the radius will be just the distance of that center to the vertices. So we need to find the center, we need to find the point which has equal distance to all 3 vertices. How can we prove that there exists this point, unique point? What does it mean to have equal distance to A and B and to B and C, geometrically speaking?
It means that the point is in the perpendicular bisectors of BC and AB.
Yeah, so the point has to be on the perpendicular bisectors of AB, BC, and AC. But it is enough that it is on 2 of them, it will be automatically on the 3rd one because of the equalities. And if you remember, this is exactly the proof that we did with 3 radical axes are concurrent. The radical axes, when we have 3 circles, the radical axis of two of them gives equal power to circle 1 and circle 2. The second radical axis gives equal power to circle 2 and circle 3. So automatically you have equal power in all three circles at the intersection of the radical axis. So this intersection must also be on the third radical axis. So the same thing you can do with perpendicular bisectors. And in fact, it's a special case because you can think of points themselves. If you think of sort of like small circles at these points of equal size, you can even think of them at zero size, degenerate circles. It doesn't matter. You can think of them as degenerate circles at these points, or you can just think of them as circles of the same size. But they don't have to be small. They can just be, any circles with the same radius. That's the point. Centered at A, for any value of R. Circle centered at A with radius R, circle centered at B with radius R, circle centered at C with radius R. What are the radical axes? They are the perpendicular bisectors. So proof is perpendicular bisectors of segments AB. Well, these segments, AB, AC, BC are concurrent. These perpendicular bisectors are concurrent. And this unique point is to be called O. And at the center O, there is this unique circle passing through ABC. Why are these concurrent? Let's just write because intersection of any two of them has equal distance to all three vertices. All three vertices. This is a special case of radical center. When we think of circles centered at A, B, C with equal radius, equal radii. Right? When you think of circles centered at these points with equal radii, the radical axes are the perpendicular bisectors, and they intersect this is the radical center. The radical center is the general case of this. So here we are just doing this special case with the same logic, with the same proof. When you intersect two of them, the intersection already satisfies. It has three quantities equal to each other. So the third line must also go through this. So this is the proof. Okay. The next thing I want to talk about is centroid. Centroid is the point G such that AG, BG, CG are all medians. So all medians are concurrent. Okay. So when you connect them to midpoints, KLM, these are concurrent. And there are the famous ratios. AG is 2 times GK, for example. BG is 2 times GL, etc. So again, how can we prove this? Well, there are many proofs. You can certainly prove this. But I want to show you a proof which by itself is valuable. Not for the sake of proving this only, but to really understand a more general abstract concept in geometry. Well, the statement is there exist G as shown. Proof. I want to define G immediately as the average of the points. Well, first of all, what does this even mean? Have you seen anything like this? This is not something common. This is not something...
Yeah, I don't know this one.
Yeah, Andre did this, right, with you?
Yeah, I think we can prove it using Shiva's theorem.
Well, yeah, that's right. But in general, have you seen a notion of taking a linear combination of the points like this, multiplying points by coefficients and adding them? Weighted averages of points. So here, A, B, C. Here I'm talking about points in the plane. I'm talking about some general concept. Like these are called affine combinations, or they are called weighted averages. The same thing. As a general concept, okay?
I think that this is like the center of these points with the weights that we brought.
Yeah, it is the center of mass.
Exactly. Yeah, this is center of mass with the equal weights. This is called weighted average or center of mass with the given masses or affine combinations. The general notion is this: given points in space, it can, well, in this case we are doing it in the plane, points a1, a2, an, and given real numbers w1, w2, wn, real numbers such that their sum is 1. If their sum is 1, then the expression, you can have a combination like this, w1 units of a1, w2 units of a2, plus wn units of an. This expression defines a point. And this is what you know as the center of mass. This always defines a point. And the way you can think of how to define this point is you can just put coordinate system and replace the points by their coordinates. But the idea is because their sum is 1, even if you change the coordinate system, even if you change the origin of the coordinate system, you shift them by a constant, and this expression is shifted by the same constant. So you still get the same point geometrically. This is why the summation equals 1 is important. For example, you cannot have something like 2 times a. There is no 2 times a point, right? When you have a point, there is no 2 times a point. Where is 2 times this point? There is no such thing. But there is always a plus b plus c over 3, a plus b over 2. A plus b over 2 is, for example, which point?
It's just the midpoint.
It's the median, the midpoint.
Yeah, it's m. So therefore, now defining this point G, wherever the point happens to be, I can write this equality as 1 over 1 over 3a plus 2 over 3k, because k is b plus c over 2, right? So this is b plus c is 2k. This k is b plus c over 2. So this means G is on the line AK. This automatically means G is on the line AK with, since there is more weight of K, it is closer to K. and the weight of k is twice, so it means this length is twice this length.
We can also show it through vector addition. When we had some problems that Andrew gave us, I solved them using vector addition.
Yeah. This is just the same thing. Yeah, this is just the same thing. So this is affine. Affine space. So when you learn about abstract algebra later on, if you study mathematics, you will learn abstract algebra, and you will see there is the notion of a vector space and there is the notion of an affine space. They are very similar, except the difference is that in affine space there is no notion of zero. So you cannot just add with any you can add, but you can add with weighted coefficients adding up to 1 in the affine space. So in geometry, of course, you can choose an arbitrary origin, and you can pretend you are doing a vector space addition, or you can directly do the more abstract notion of affine space ideas without choosing an origin. They will come down to the same thing. So this weighted average and center of mass things is really from affine geometry. From the point of view of our Euclidean Olympiad geometry, affine geometry is just one sort of, let's say, very basic layer of geometry. So most other notions, such as circumcircle, for example, circle cannot be even defined in affine geometry. So Euclidean geometry is richer. Affine geometry doesn't have much in it. It only has these things. But this is part of Euclidean geometry. So affine geometry is part of Euclidean geometry. And it is interesting to know that some of the things are just affine geometry. Some of the things like Menelaus theorem, Menelaus theorem is really just affine geometry, for example, and Cheva's theorem, as you said. So these are part of affine geometry. So part of the Euclidean geometry in which angles don't matter, and you don't have circles. You only have lines, and you only talk about intersections of lines and ratios of the lengths on the same line, but you don't compare the lengths of segments which are not parallel to each other. If you do geometry like this, very basic notion of geometry, this is called affine geometry, and you can do it with these things. This is one layer. So this is why I wanted to show this to you. So this shows that G is situated like this on AK, and similarly, this immediately shows, as you can see, this is a proof that there exists a point G which satisfies this. Similarly, and what you're saying at hand with vector addition is just another formulation of the same thing. All right. So this is the proof, and we can even do this with 4 points, for example. We obtain interesting things, by the way, just as an aside. Further discussion. When we have 4 points, given A, B, C, D, they can be at the vertices of a convex quadrilateral, or they can or it doesn't have to be like this. They can also be concave. I'm just doing this for the sake of the figure. Let G be, for example, the average, again, with the same weights. So I can write this as, for example, A plus B over 2 plus C plus D over 2 divided by 2. What does this tell me? It tells me that the midpoint of AB, let's call it X, and the midpoint of CD, and this is the midpoint of XY. This point G is really the midpoints of the midpoint of the segment joining the midpoints. But you can also do it from here, from these midpoints, K and L, right? So let's do this one in blue. Let's do this one in green. And we can also do the third one, which is midpoint of AC and midpoint of BD. As I said, the situation, well, how the points are situated, it doesn't matter at all. So midpoints of these are like that. All of them must have this common midpoint. Let's call them P and Q. Yes, similarly, yeah, what I'm saying here, this is also equal to K plus L plus 2, and also equal to P plus Q over 2. So segments XY, KL, PQ share their midpoints. By the way, do you know what happens when two segments share a midpoint? When two segments have the same midpoint? Does this remind you of something?
Yeah, the 4 points form a parallelogram.
Parallelogram, exactly. So this is an alternative way to prove this. So this is a very nice fact of quadrilaterals. In my opinion, this is the basic fact of quadrilaterals. The most basic configuration about quadrilaterals. Although right now I'm doing triangles with you. If we had a lesson on quadrilaterals, this would be the first thing that I would teach. The basic thing is that when you take the midpoint of a segment and midpoint of the opposite segment and join them, the midpoint of this is common in all three ways. The blue way, the green way, and the red way, they all have the same midpoint, and this gives us parallelograms. But alternative way to prove the parallelograms is directly, you can prove like KX is parallel to BD, and KX and LY are both parallel to BD. And LX and KY are both parallel to AC. So KX LY is parallelogram. So KX from the midpoints we can find this, but we can also find this directly, right? So this is what I'm saying. So this shows that KX LY, PX QY, and PKQL are parallelograms. We can also prove this directly without. We can also prove this directly. Directly as, for example, KX is parallel to BD, and this is parallel to LY, and KY is parallel to AC, this is parallel to LX, etc. So this is the basic fact. These parallelograms are the basic facts of triangle, of quadrilateral geometry. These three parallelograms. This is the most, I think, basic configuration of quadrilateral geometry. You can prove it directly, but it's also nice to see that it can be proven through this affine geometry and the notion of centroid in a quadrilateral. All right, so let's continue with triangle stuff. Let's pass to the discussion of orthocenter. Do you want to say anything about this before we move on? If not, let's look at orthocenter. But I will not only discuss the orthocenter because there is actually, as soon as you think about the orthocenter, there is a notion that you should think about as well. The notion of orthic system. Let's call it orthic system. The name can change, I guess. It can be called orthogonal system or orthic quadruple, etc. Alternative names. I'm gonna come down to what this is. First, let's talk about the orthocenter. We know what the orthocenter is. So this will be the second thing that I will discuss after discussing the orthocenter. The orthocenter is the intersection of the altitudes, right? The three altitudes are concurrent. Again, you can prove it in various ways, but the statement is the three altitudes are concurrent. But this is there is a nice proof that I want to give there to observe them as radical axes. Maybe you can try to find this. Find some circles for me such that these are radical axes. So automatically they will be concurrent. The orthocenter will be the radical center. So I want you to define three circles for me in terms of ABC. So in this case, for example, the three circles we defined were at center A, B, and C with equal radius. This gave me perpendicular bisectors as the radical axis, so it gave me the circumcenter. But if I define the three circles in a different way, I can somehow get the altitudes as the radical axis and orthocenter as the radical center. Defining these three circles will automatically be the proof that the three altitudes are concurrent. Can you try to think about this?
I think they will be maybe the circle with diameter AC, BC, and AB.
Exactly. So altitudes are the radical axes for the circles with diameters AB, AC, BC. This is just a proof. And how can we see this? Let's just draw the picture of this. Well, if you draw the altitudes, so since we want to show that they are concurrent, I don't want to draw that they are concurrent. I just want to draw the altitudes like this without seeing what happens in between. Okay. These are the feet of the altitudes. So the diameter, circle with diameter AB is this one. Circle with diameter AC is this one. So intersection is A and K. So AK is the radical axis, as you can see. And circle with diameter BC is this one. So for these two, AK is the radical axis. For this two, BL is the radical axis. And for this two, CM is the radical axis. They have to intersect. And what is an orthic system? The nice thing is, as soon as you get a triangle and its orthocenter, if the triangle is not a right triangle, if you have a right triangle, the orthocenter is the right vertex. But if it's not a right triangle, the orthocenter is a fourth point. What you see is A is the orthocenter of HBC, and B is the orthocenter of HAC, and C is the orthocenter of HAB. It's not only that H is the orthocenter of ABC. Any one of these points is the orthocenter of the other 3 points. So none of the points is special. In some sense, this gives us a structure with permutation symmetry, sort of. And this is very useful in many cases to think about this, okay? An orthic system well, just learn about the concept, but the name may not be standard. In different textbooks, they can give different names to this. An orthic system consists of 4 points. 4 points A, B, C, D, such that when you join any two of them and the other two of them, they are orthogonal. So AB is perpendicular to CT, and AC is perpendicular to BD, and AD is perpendicular to BC. These facts hold. But notice, if two of these is correct, then the third one is automatically correct. If two of these holds, third automatically holds. Because if, for example, these two holds, then you can think of the triangle ABC, and this gives you that CD is an altitude and BD is an altitude. So D must be orthocenter, so AD must also be altitude. So if you just take any two of these, but as you can see in these statements, the 4 points play an equal role. You just connect two of them and you connect the other two. They have to be orthogonal. And there are three ways of doing this. There are three ways of connecting 2 points and connecting the other 2 points, like what we did with quadrilaterals here. When you do AB and CD, when you do AD and BC, when you do AC and BD. So if we have two of these orthogonalities, the third one is also orthogonal. This is equivalent to saying, this is the definition of an orthic system, equivalent to this is equivalent to the following, to any of the following. As an alternative definition, A is the orthocenter of BCD. B is the orthocenter of ACD. C is the orthocenter of ABD. And D is the orthocenter of ABC. All of these are equivalent statements. All four statements are equivalent because they, if you expand them, they are both equivalent. All four of them are equivalent to this. So this is the notion of an orthic system. So whenever you think of a triangle and its orthocenter, it's somehow good to think that these 4 points form an orthic system. Although in most cases we just focus on the triangle and the fourth point plays a special role, and this is why we denote it by a letter not in the same family. So for the vertices of the triangle we use ABC, and for the orthocenter we use H. When we use this notation, it doesn't show us that they play an equal role. So it gives a special role to point H and special role to triangle ABC. But sometimes somehow one of the triangles HAB or HBC or HAC also play a role in the problem. So it's good to think that whenever there is a triangle and its orthocenter, there's actually an orthic system. And you can look at the orthic system in 4 different ways. This is what I wanted to show. So since orthic system is a system of 4 points, we can also use this basic knowledge about quadrilaterals in the case of orthic system to see whether something special happens or not. So these 3 parallelograms. Does anything special happen with these 3 parallelograms? If ABCD is an orthic system, of course, an orthic system is always a concave figure, but here it doesn't matter. So I can also draw a concave figure. I mean, whether orthic or not. Let me draw it in a way that it's not orthic, just for the sake of picture. But if it is orthic, my question is, does anything special happen? So I'm going to use the same names like X, Y is this one, and K and L. K is this one, L is this one. This is Q, and this is P. So the red one here is this one. The green one is this one. The blue one is this one. So still, you see, just an alternative picture for the same theorem. So I don't need to prove it differently. It's the same proof. Still, these are parallelograms, like xk ly is a parallelogram, for example. xk, well, xp yq is a parallelogram, and qkyl, no, qkpl is a parallelogram, etc. So G is the common midpoint of P, Q, K, L, and XY. So when this is an orthic system, do you see anything special with G or with the parallelograms? And this will be the when you see this, this will be the fourth information about triangles. In fact, it's an information about orthic systems, but it becomes an information about triangles as well, because it, from a triangle you construct the orthocenter and the orthic system. Yeah, the answer is actually something special happens. Think about the proof of parallelograms in this way. And think that ABCD is an orthic system.
What's the why? What are BQ? What is the definition of this point?
Wait, P is the midpoint of AC and Q is the midpoint of BD. And G is
So,
the midpoint of PQ.
okay, Q is the midpoint for.
Q is the midpoint of BD.
Ah,
So always when we take a segment like AC, the opposite segment is BD. If I take AB, the opposite is CD. If I take AC, the opposite is BD. And if I take
yeah.
AD, the opposite is BC. But here's the general proof that these are parallelograms. If you further know that we have an orthic system, this means that AC and BD are perpendicular. By definition of the orthic system, AC and BD are perpendicular. So AD and BC are perpendicular, AC and BD are perpendicular, and AB and CD are perpendicular. All these three are perpendicular. If BD and AC are perpendicular, this means KX and KY are perpendicular, LX and LY are perpendicular, KX and LX are perpendicular. What does this mean about the parallelogram? The sides are perpendicular in a parallelogram. This is called.
Isn't that the rhombus?
No, not the diagonals are perpendicular. The sides are perpendicular.
That's just a rectangle.
Yeah, it's a rectangle. So in the case of an orthogonal system, these three parallelograms are rectangles. And so in general, these are parallelograms. So these are the three diagonals which share their midpoint. But if they are rectangles, what can we say about the diagonals? What can we say about the diagonals? In a rectangle, the diagonals are what?
In a square, they're perpendicular.
Yeah, but in a rectangle,
They're equal.
yeah, they are equal length. So this is very good information. In the case of orthic system, XY, KL, PQ are of equal length. They not only share their midpoints, but they are of equal length. So let's write this information. Okay, this is the fourth thing. In an orthic system, well, let ABCD be an orthic system. Orthic system. And as before, let's define the midpoints. So this time let's define the orthic system nicely. So let's draw it. Let's draw it realistically. And let's look at the midpoints of these. So as I said, so there are these 6 midpoints, 6 segments and 6 midpoints. What names did I give them again to remind myself? X, K, P. I called them like this: X, K, P. So if this is X, this will be called Y. Make them black, and then this midpoint I should move up a little bit for a better picture. This will be Y, this will be L, this will be Q. So this is the red one, this is the blue one, and this is the green one. Yeah, actually L should be moved here. Okay. So in an orthic system, this point, like now let's call it N because it's customary to call it N. Let N be. In the case of an orthic system, it's usually called N, and you will see why it's called N. So this is just the centroid of the 4 points. Okay, center of mass of the 4 points with equal weights. N is the midpoint. N is the common midpoint, as usual. Common midpoint of midpoints. Common midpoint of. Sorry, midpoint of KL, XY, and PQ, which have equal length. So this is because of the orthic system. This equal length because of the orthic system. Otherwise, they in general they don't have equal length. Still, there is a common midpoint for these 3 things in general.
Why should they have the same length?
Yeah, the proof that they have the same length is this. Well, proof is to show that these are rectangles. So KX is parallel. So K is the midpoint of AD and X is the midpoint of AB, right? KX is parallel to BD. And this is parallel to LY. And all of these are perpendicular to the other things that are parallel to AC. What's parallel to AC? KY and LX. So this shows KXLY is a rectangle. KL equals XY. If you look at the figure, the reason that this is a rectangle is KX is parallel to BD and LX is parallel to AC. So KXL is 90 degrees.
Yeah.
Yeah, this is why this is a rectangle, so the diagonals have equal length. KL equals XY. Similarly, PQ is also equal. So this is the common point of 3 segments which have equal length. In the case of orthic system, this is what happens. So this is a very special thing. So if I take this in a box, therefore, therefore, there is a circle at the center N passing through all 6 points. So these 6 points are in a circle with center N. Because NK, NL, NQ, NP, NY, NX are equal. K, L, X, Y, P, Q are on a circle with center N. So KL, XY, PQ are diameters. So since these are diameters, there are more points that you can easily derive from the figure to be on the circle. Namely, the intersections of, namely these 3 points are also automatically on the circle. Let's call them, let's give them different names, like EFG, for example. Let's call them EFG. If we call them EFG. As we observed, there is this blue. So from the midpoint of this to the midpoint of this. And there is green one from the midpoint of this to the midpoint of this. And there is the red one from the midpoint of this to the midpoint of this. Well, let's not make them red. So this circle, and there is this circle from them, right? So there is this circle passing through these 6 points. But this circle will also pass through these other 3 points. Let's make them actually orange. Why? Because of the 90 degrees. So these are 90 degrees because of the orthic system. Since the green one is a diameter, so we have 2 green points, 2 blue points, and 2 red points. So these are opposite midpoints, okay? Blue points are midpoints of their segments. So this blue is the midpoint of AD, this blue is the midpoint of BC. They are opposite. So this red is the midpoint of AB, this red is the midpoint of CD. This green is the midpoint of AC, this green is the midpoint of BD. So green segment, blue segment, red segment are diameters of the circle. So necessarily these 3 orange points also come. This orange point comes because of the green. This orange point comes because of the blue segment. And this orange point comes because of the red. So there is this 9 points. This is called, yeah, let's not call them anyway, let's not call them GFK, but let's just, so this is called the 9-point circle. This circle is called the 9-point circle because of this. Because of this figure, 9-point circle of the orthic system. So the subject that I wanted to tell you is this 9-point circle. And this is why it is called N from 9, since this is the center. So given any orthic system, there is a 9-point circle. And they usually teach this as subject of a triangle. Given any triangle, if you put the orthocenter together with the triangle, this becomes an orthic system, and you can draw the 9-point circle. This 9-point circle goes through the midpoints of all 6 segments, and it goes through the 3 feet of the altitudes. So 6 of the 9 points is segment midpoints. 6 plus 3, 96 plus 3. 3 points are the feet of the altitudes, and 6 points are the segments, midpoints, segment midpoints. This is a famous thing, and the center of the circle is the centroid of the center of mass of the orthic system. Okay. So this is pretty good information about an orthic system. So so yeah, the title of this should be 9-point circle. Nine-point circle. Okay, we learned about, after learning about the orthocenter, we learned about the 9-point center. 9-point circle. The good thing, so if they talk about the 9-point circle of a triangle, don't forget it's just the 9-point circle of the orthic system. In fact, so the 9-point circle of ABC and HBC, HAC, and HAB are the same circle. So for all these 4 triangles, it's the same orthic system, so it's the same 9-point circle. And the next thing, okay, there's more stuff to learn. Maybe we can stop here and continue the rest in the next lecture, because the next thing I want to teach you is about the angle bisectors. Intersection of the angle bisectors, which are centers of the circles that are tangent. Okay. There are 4 such centers from the internal. If you don't distinguish between internal or external bisectors, consider all of them. There are 4 such centers, 4 such circles that are tangent to all 3 sides. And these 4 centers also form an orthic system. So think about this. Once you draw this figure, you will see the orthic system, and think about what's the 9-point circle of this orthic system, for example. So this is really a good figure. This will be inshallah for our next lecture. I will decide whether it will be tomorrow or the day after, hopefully. Does it make a difference for you?
It doesn't matter to me.
Okay. Okay, I will let you know through the other colleagues, inshallah. Muhammad or Tahsin. I will let you know to decide whether. But the same link should work, okay? The same link should work. So it will be either tomorrow or the day after, inshallah. Do you have any question?
Could you give us some exercise in geometry?
Yeah, that would be good. Okay, I will try to put it up and send it to you. Okay, put up the problem and send to you.
Thank you.
You're
Thank
welcome.